Hello everyone, we are looking at an old radio. When you turn this knob, it tunes on the old radio stations. We're looking at it because this is a good example of all the things that we're going to look at this year as far as electricity and magnetism. Alright, now if we look at the circuit here we've got some resistors and capacitors and transformers and diodes and all kinds of different stuff in this thing here. So far we've studied circuits, series and parallel, and we know what these little things are here. These are the resistors with their color code on them as well. Over here we've got the knob that adjusts the volume. When you turn the volume on a radio, what you're actually doing is changing the resistance of a resistor. We call it a potentiometer. And it is what makes things loud and soft. And there it might have one for the tone, etc. on there. All right, the next thing that we're going to study are capacitors. And down inside here, there's all kinds of capacitors. Here's some over here, a capacitor. Here's a capacitor. This thing right here is a capacitor too. That's what does the tuning. All right, there's other things in here too as well, some coils, transformers, and diodes and things like that, and we'll learn about that stuff more later. All right, what we're going to learn next is capacitors. What are capacitors? So what are capacitors? Capacitors, like resistors, are small electrical components that we use in circuits. Their main purpose is to store charge. All right, similar to like a battery, but batteries work on a chemical reaction, whereas capacitors store charge just by moving around electrons. All right, here's some examples of capacitors. They're just little devices that can store charge. All right, on a circuit like this old radio, here's a capacitor. Here's a capacitor. There's a bunch of capacitors. There's some resistors with their color code and such on there. All right, now, if we took one of these things apart, what would it look like? Here's a capacitor that we tore apart, very similar to this one right here. All right, here's what we found inside. It's kind of like a sandwich. Notice that there's this piece of metal and then a couple of pieces of, looks like cellophane paper and some regular paper, and then another piece of metal, looks like aluminum foil, and then some more pieces of paper. And the whole thing is sort of just rolled up like this. And every capacitor has two little electrodes, and each one of those electrodes just leads to one of these two pieces of metal. One there and one there, two different pieces of metal. So essentially a capacitor is just two pieces of metal. All right, here's a similar kind of situation. These are pieces of aluminum, all right? And I could make a capacitor just by taking this piece of aluminum and creating kind of a sandwich out of it and having the two pieces of metal separated by some sort of insulating material that doesn't conduct electricity. All right, to store charge then, what happens is that we'll have to take electrons out of one and put them into the other. So then the capacitor will store up charge, positive on one plate, negative on another plate. And then the whole thing could be rolled up and inserted inside of a container like this. All right. Some capacitors are really tiny, like this one right here. It's just got two little disc plates that are separated by some material. Other ones got long strips rolled up inside of a container like that. There's lots of different ways that you could do it. All right, here's an illustration that kind of shows the construction of a capacitor. It's basically two metal plates, and we hook up a voltage source like a battery to it, and we can make electrons come out of one plate and flow into the other plate, and we charge up the capacitor. All right, now later we will learn about how these things are constructed a little bit more and look at this equation right here where that tells us how to determine what's called the capacitance of the capacitor based on the area of the plates, the distance apart, and some other parameters too as well. All right, the main equation governing this is this right here. Q is the symbol we use for charge. V for voltage or EMF, and then C is a measurement called capacitance. Now, what is capacitance? Now, capacitance really is how well that thing stores charge. It's the ratio of the amount of charge to the voltage. So when I put a voltage on here, I create a certain amount of charge in the capacitor, and how much charge I make, of course, depends on the capacitance. If I make a bigger voltage on here, I'll get more charge. Bigger voltage, more charge. The ratio of the charge to the voltage is that quantity we call capacitance. All right, so capacitance would be measured in coulombs per volt. Coulombs per volt. We're going to give a special name to a coulomb per volt. We're going to call it a farad, after Michael Faraday. So capacitance, which is how we measure capacitors, is measured in a unit called the farad. This equation then tells us how everything is related. The charge on the capacitor, Q, is its capacitance times the voltage that is applied to it. Later we'll learn that there's an electric field that is in between the plates that will go from the positive plate to the negative plate, and we'll study electric fields more later next semester like that. For now, we'll just treat the capacitor as though it's some kind of a electrical component that can be part of circuits. Now, back when we studied resistors, we talked about how you could put resistances in series and parallel. All right, you can do the same thing with capacitors. The symbol for a capacitor in a circuit is two parallel lines. All right, so these are your capacitors. And if sometimes for a voltage source, we'll have a short line and a long line, and that is a plus and a minus. So for capacitors, it's two lines that are of equal length, and there's really no charge on it until you put a voltage source to it. All right, now if I put some capacitors in parallel with each other, then essentially what I'm doing is creating larger plates. All right, so all these three capacitors right here are hooked in parallel with each other, and if I had one big plate that kind of went across like that, I would just have one big capacitor. So putting them in parallel sort of creates more capacitance. Now remember, when we put resistors in parallel, we have to do the reciprocal of the sum of the reciprocal. But when we're putting capacitors in parallel, we'll just add them together, like when resistors in series. All right. Now, some other things apply. The voltage across the capacitor in parallel is going to be the same for all of them. So the voltage across here, if I put a voltmeter here, and I put a voltmeter here, and I put a voltmeter here, they would all read the same thing. They're in parallel with each other. So that's still true on that. The voltage across all the parallel capacitors will still maintain to be the same thing. All right. Now, the total capacitance then will be the sum of the individuals. All right. Each one of them is going to have a certain amount of charge on it, Q, that depends on the capacitance and the voltage that is applied to it. So each one of these will have a different amount of charge if they're different size capacitors, but they'll be at the same voltage, each one of them as well. Now, the total charge of the whole circuit then will be the sum of however much charge is on each one. Now, in series, however, if I try to charge up the first one by putting electrons into one side, electrons will leave the other side and go into the next one. And then electrons will leave the other side and go into the next one, and so on. So electrons will flow until these things become charged up. Once that has happened, the current will stop flowing. They'll reach a certain amount of charge depending upon what that voltage is we put it on there. All right. They still will divide the voltage, each one of them. If I put a voltmeter across each one, they're all going to read something different, if they're different capacitors, that is. All right. Each one of them is going to have charge in it, but each one of them will have the same amount of charge. Reason is that if I put electrons into the first one, electrons leave the other side, the same number of electrons. So the same number of electrons are go into the next one, which will make electrons go out the other side. The same number of electrons. So each one of these will end up having the same amount of charge on them. They will have a different voltage on them, but if they're all the same capacitor, they would have the same voltage. But no matter what, they will all have the same amount of charge on them. It kind of a weird concept there, because the charge leaving one goes into the next. So however much leaves one will be how much goes into the next. So they will all end up having the same amount of charge, but their voltages won't be the same if their capacitances are not the same. If their capacitance are the same, then they'll all have the same charge and the same amount of voltage on it too as well. All right. Now, this voltage here, remember, is going to be just Q over C, Q over C. All right. Because if the C is different for each one, then the voltage will be different in each one, but the charge will be the same on each one of these. All right. Now, just like we could add up resistors in series, we can get the total capacitance, but now we have to do that reciprocal thing, the reciprocal of the sum of the reciprocal, all right, to get the total capacitance of capacitors in series. All right, let's take a look at a capacitor in a circuit. All right, a capacitor in a circuit. Here's a capacitor. Its capacitance is 25,000 microfarads. And then it tells us something also about it, the maximum amount of volts that we can connect to it. Now, the physical size of the capacitor is not really indicative of its capacitance. That is, here's one that's smaller. It does have a smaller capacitance, but it has a much larger voltage rating to it as well. So the actual size of the capacitor itself doesn't really indicate, its capacitance. It's related to how it's built and what you're going to use it for. All right, let's look at a capacitor in a circuit. All right, so I have over here a circuit, and that is the power source. That's right here, our power supply. All right, I'm going to turn that up. In this case, I'd want to have a maximum of 25 volts, but I'm going to turn it up to, let's say, just about 5 volts, 4.8. And then I have some wires, and I can lead right to this capacitor. And one thing about capacitors, you don't really see a whole lot of action. All right, I hook this up, and boom, instantly, almost instantly, the capacitor is charged. Now, there's no indication, doesn't light up, doesn't get warm, doesn't hum, doesn't do anything. All right, the current will flow, and it will get charged up. Notice that the current here is 0. So once it's charged, the current stops flowing. All right, the current stops flowing through it. All right, now if I unplug these two things, the thing is still charged up. If I touch these two together, almost instantly I discharge it. And again, we don't see anything on there. Let me charge it up one more time. All right, did you see the light flash there? A momentary flash of current happens. All right, discharge, and watch the little thing. It gives me a little bit of current there for a very short period of time. The thing is charged. All right, now here's a light bulb. I could take that charge, put it into a light bulb, and it'll light the light bulb. And then very quickly, it totally discharges. All right, now, not instantaneously. It takes a little bit of time for the current to go through and run all that charge out of there. All right, let me charge it up one more time. All right, quick charge, a quick discharge, and just a little flash of light. All right, quick charge, a quick discharge, and we can see a flash of light on there. All right, so how long did it take to charge the capacitor? Well, that will depend on the resistance. It'll depend on the resistance. All right, if there's a lot of resistance, then it's going to take a while for the electrons to flow around the circuit and bring this thing up to charge, and then there's a field in between the two plates, like that. If I have a bigger resistance, it will take a longer amount of time. If I have no resistance, it will be almost instantaneous. So the wires we think of as having almost zero resistance. So almost in an instant, it charged up the capacitor. Let's take a look at these graphs. We have one graph, I versus time, current versus time, and another one, voltage versus time, voltage versus time. All right, now when I first connect this circuit, all right, or if I had a switch, turn on the switch, current will flow from plus to minus. Electrons will go in, well, let's just say the current flows into this, current flows out and around like that, and the capacitor starts to charge up. All right, now realize that, notice that the capacitor looks like there's a gap there, and capacitors actually behave as though they're an open circuit, at least once they're charged. All right, when they as they're getting charged, it appears that current flows, but once they reach charge, then the current will stop. All right, that's why we said it's kind of instantaneous. Now, if I put a resistor in there, that'll take amount of time. Now, how much current would flow? All right, I have here an EMF, which is some sort of voltage source. So the amount of current could be figured out by doing Ohm's law, in this case, EMF divided by R. So that's how much current would flow. It's just based on the resistance and the voltage source on there. So right when you close the switch or connect the circuit, a certain amount of current's going to flow, and then the capacitor will get charged, and it will take a certain amount of time. So on this current versus time graph, we're going to start off, let's call it I0. All right, it's going to be I0, and then that I0 is going to be equal to the EMF divided by the resistance. All right, that's how much current's going to flow right at first. And then over time, the current will drop down until it stops once the capacitor is fully charged, like that. All right, so current versus time graph would look something like that. Now, if I had a larger resistor here, that would stretch out the amount of time that it takes to charge, but still it would start off, it would probably start off at a lesser current because, and then it would start off at a lesser current and then swoop down and take a longer amount of time on there. If I had a smaller resistor, then the current would start out higher and then it would reach charge a lot quicker on there as well. All right, so how long it takes to charge up the capacitor depends on the resistance, and how much current actually flows depends on the voltage source and the resistance, but the time it takes depends on the capacitance. All right, the capacitance. Now, looking at the voltage graph, what would that look like? What would that look like? All right, when we first connect the circuit, all right, when we first connect the circuit, current is at its maximum, and it's flowing through the resistor, and it appears to flow through the capacitor, all right, as electrons move. It appears as though realize that no electrons move across the gap here. All right, no electrons move across the gap. There's an electric field that pushes electrons out of the other side, but no electrons actually flow across the gap. It kind of appears as though that happens, but no electrons actually pass the gap. But right at first, the current is high. If I put a voltmeter across the resistor, it's going to read whatever the voltage source is right there. If I put a voltmeter across the capacitor, at first, it will measure 0, and then eventually all of the voltage is going to drop across that open spot in the circuit. And this one will approach 0, and this one will approach whatever voltage the source is. All right, so the voltage across the capacitor is going to measure some value that's equal to the EMF. Starting off at 0, it will look like this. So the voltage across the capacitor will grow to be the voltage on this, and then we can say that the capacitor is charged up to a certain voltage, and it has a certain amount of charge, and if we know the capacitance of it, we know what that ratio is. All right, the voltage of the resistor then will start out large and get smaller. So if I made a similar graph for the voltage on the resistor, it's going to start out at the EMF and swoop down like the current graph did. All right, this is an exponential growth and decay. exponential growth and decay. And we often will use E as the base and raise it to some power, maybe call it X. All right, so if I made a graph of E raised to the power of X, I would get a graph that looks like this. E, remember, is what we call Euler's number, and we often use that as a base for logarithmic type functions. We call it a natural log when we use that as a base for it. And this shape of this graph would look like this. All right, actually it will look like this. It's an exponential growth. Actually, we make the exponent negative, it would look like this kind of graph, that shape to it. So we often apply this kind of equation to this kind of growth and decay. All right, we could also do y equals 1 minus e raised to the power of negative x, and then I'll get the kind of graph that looks like this. All right, there's kind of our quick little introduction to capacitors, and then we will come back to that lab that we were looking at in class for those that came, and probably look at that next week.